All right, awesome. So we're going to get started again with the second part of the morning session. So we're excited to have Björn Gottschall here. He studied computer science at TU Dresden in Germany and worked on his master's at Xilinx and received that in 2018. Since 2019, he's been a PhD student in computer architecture at the Norwegian University of Science and Technology. So Björn, take it away.
Thank you. Yeah, hi. I'm here today to present you a tool that I wrote and that mostly was hiding behind my papers. And I think now is the time to get the word out and tell you about TraceDoctor, which is a versatile high-performance tracing interface for FireSim. So I want to start with a motivation why I came up with that. So that's me and my laptop running Spec 2017 benchmarks. And I let loose a lot of performance profiles on those benchmarks. And I found out that they all disagree. So even multiple runs of the same benchmark profiling with one profiler disagreed. And I thought, like, how is that possible? Since I'm not going into the details on why that is, spoiler, they are all wrong, which we have published in the paper Tip Time Proportional Profiling at Micro 2021. Anyway, I went to my professor and told him profiling is really, really bad. And he said, yeah, somehow everybody knows that. I'm like, we need to find a solution. So we found a solution. We wrote a paper about it. That's just a generic title. It wasn't named that way. But it was rejected. So maybe we didn't find the solution. The problem was that we didn't have the golden reference. So when you're executing a benchmark, you don't really know what is the ground truth. Which instruction take how much time, how many cycles, we don't know. So my professor told me we need a golden reference. We need to know about every single instruction, the benchmarks, we need about every single cycle. I'm like, okay, hold my beer. And that was at a time when FireSim 1.9 was released. So, I mean, this is not really new, hopefully, to most of you. FireSim, cycle accurate, full system simulator. We can simulate out of order, high performance CPUs. Can run full stack Linux environments with dock devices, networking. We can run industry standard benchmarks. So Spec 2017, we can actually run it end to end in FireSim, which isn't possible in simulators like Gem 5. So we want to know about every single instruction, every single cycle. We don't want to use any functional models. We don't want to have use statistical sampling and no sim points. We really want to know all instructions, all cycles, end to end for Spec 2017 benchmarks or alike. So tracing in FireSim. FireSim comes with two tracing interfaces. One is, or not really tracing interface, but one is autocounter, which can provide statistical data for any signal that you're interested in. Really useful. And TracerV, which traces out all retiring instructions out of your simulation, can save it in binary, text, or the flame graph FirePerf format. It supports triggering when you're just interested in a very small time frame of your simulation. And it generates about 64 bytes per cycle in a binary format. So let's take an example. Let's take Spec CPU 2017 P waves on the 4-byte sonic boom. It's 2.8 trillion dynamic instructions. We need around 6.8 trillion cycles. And that generates around 433 terabytes of trace data. So that's not really the solution to trace. And this is just one benchmark, right? We want to do this for whole Spec 2017. So then I come up with TraceDoctor. So TraceDoctor can attach to basically any signal that you're interested in and trace it out every single cycle. It utilizes a buffered and parallel host framework to process this trace data. It has a flexible worker design, which enables efficient and highly customizable trace processing. And we have used it to analyze more than 300 trillion cycles and 292 trillion dynamic instructions, and we parse for that more than 4.3 petabytes of data. So I want to explain to you how TraceDoctor works. So on the right side, we see the FPGA, which has our target system in the target system clock domain. And similar also to TraceAV, we have the TraceDoctor bridge, which has a trace vector and a valid signal. So the designer can attach this trace vector to whatever signals you're interested in. This trace vector also has a variable size that you can set to whatever you want. And it has a valid signal. As soon as that goes high, this trace vector is traced out. And for this host decoupling, right, the TraceDoctor bridge has this ready signal, which it can use to disable the clock of the target system. So this trace data is transferred over DMA to the host TraceDoctor driver, where it is put into a buffer queue. The buffer queue has also variable size. You can set as many buffers as you want. You can also group buffers together. And those buffers are then distributed to so-called workers. And every worker by default runs in its own thread. So parallel to the simulation, as soon as the tracing data has been transferred to the host and put into the buffer queue, simulation is allowed to continue. And the threads are picking up those buffers and distributing them to the workers. The workers are the final part of this tracing interface that makes sense out of your tracing data. So it is really important to write sensible workers that chew through tracing data in fast and efficient ways. So I want to show you how we can write one of those workers. And this is going to be the first and last source code in this presentation, at least. And that's it. That is a full worker. At the top, we see the constructor, which doesn't really have any code. It's just calling the parent constructor, giving it a name. And you can also see that you have here a vector of arguments. That means every single worker can be provided with individual arguments. And some trace info that tell the tracer, for example, how many bytes each DMA token, how many bytes each cycle is going to transfer out. And then the TraceDoctor interface provides this worker with the trace data over the tick function, which gets the data in and also how much data there is. And here we write this data just out to a file, which we have here requested to the parents. So that means whenever this worker is instantiated, it expects one file as output. And this file we can pull in here and write our trace data to. And that's all. This produces the exact same output as the TraceAV in binary mode. So how can we use that worker? We add this to the command line. This instantiates our worker when the simulation starts. And as you can see, that one file that it expects, we can provide here. If it would expect more files, we just add it with a comma. And we have here the ID, which is the ID of the tracing interface, when in case we have multiple cores, right? We have multiple trace interfaces for each core. So we would also instantiate automatically more of those workers, each creating a file with its own ID. So yeah, it's a name, that's the output file. So how about automatic output compression? That's super easy and automatically handled when you add a compression extension to your file. So that was easy. And let's test the performance evaluation. So what we have implemented here? We have a 4-byte sonic boom running at 3.2 gigahertz. on the Xilinx Albeo U250. We have implemented that design with 70 megahertz, running a build root Linux 5.7. For this test, we only execute a smaller benchmark NAP with test input. We use TraceRV to trace over 7 billion dynamic instructions and over 16 billion cycles. And we have tasked TraceDoctor to the exact same thing. So we have attached TraceDoctor to the exact same data. I've implemented a text, a flame graph, and a binary worker doing the exact same things. And to make everything fair, both tracing interfaces are going to write to def null to not create any more disk latencies that would impact this evaluation. So here we can see the average simulation slowdown when you do a binary text or flame graph output with TraceRV, and you can see it's slowing down quite drastically with up to 80% simulation frequency, and TraceDoctor up to 5%. So let's have a look at a little bit more detailed what's going on here. So we do the binary output. Here we have the heartbeat, basically telling us the effective simulation frequency over our simulation. We have used triggers so that we execute the boot and the shutdown time of Linux in the tracing. And TraceDoctor, by the way, can just attach to the TraceRV trigger, no problems. And now we run the TraceRV to trace out all retiring instructions in binary output form. And you can see as soon as the tracing starts, the simulation frequency drops to below 10 megahertz. With TraceDoctor, simulation frequency stays nearly up at the no tracing simulation frequency of around 55 megahertz. And by the way, we do not reach the implementation frequency of 70 megahertz because of all the host decoupling that's going on. That's kind of the expected output. With the flame graph output, TraceRV is doing much better. So TraceRV can, because it's creating much less output, it's creating just 122 megabytes of a text file with the flame graph informations. And this means TraceRV is slowing down the simulation not so much. But TraceDoctor can reach nearly the original simulation frequency without tracing. And the next is text output, and that's actually much more interesting. Similar here, TraceRV is reducing the simulation frequency quite dramatically. In the beginning, it's keeping it up because here this is a phase of the benchmark where less instructions are committed. And so TraceRV has to create less output to the text file. But we can also see that TraceDoctor is not really keeping up here. And this I have found out is simply due to the printf formatting of in numbers as text. So even TraceDoctor does this all in parallel to the simulation, right? TraceDoctor at some point fills up its buffer queue with all the tracing data from the simulation. That meaning if the buffer queue is full and the workers went fast enough to work through the buffer queue, TraceDoctor also needs to stall the simulation because the trace data is just coming in too fast. And this is what's happening exactly here. So here the buffer queue is full and TraceDoctor needs to stall the simulation because the workers went fast enough to keep up. And this is simply because we format the output with printf, and printf is really slow. But we can instantiate 3 workers and distribute the work over 3 workers, doing basically in chunks the output. And with 3 workers, we can keep up the simulation frequency nearly at the simulation frequency without tracing. And after the simulation is done, the 3 workers have each created their own text output file, and you can just merge it together and get the exact same file as TraceRV. Okay, so let's get back to the golden reference. Spec CPU 2017 with reference inputs executes around 52 trillion dynamic instructions. That means the tracing data is still in the order of petabytes of storage. This is just the Amazon S3 pricing. That means we would still need to pay like $21,000 per petabyte per month. That means performance is not the only thing that's important. So what's the solution? The question is, do we actually need to trace every single dynamic instruction? Performance profiling is about what instruction needs time, what function needs time, which application consumes time. So that means we do not really need the exact order of the retirement of the dynamic instructions, like you would have in the trace file after you run trace-ID. So the solution is we aggregate the traces on the fly while the simulation is running and sum up in a table for every single instruction address the important metrics. For example, the time that the instruction took on the CPU. And this we call the golden reference for performance profiling. And here's just an example of the top 10 instructions from the Spec CPU 2017 lab with the reference input, where you can see like how much time every single instruction took. And the golden reference is recording a lot more than this. It's just an example. So yeah, I was happy. I want to show you a different way of looking at this data. Since we have the golden reference, we can record a lot of interesting data for the whole Spec CPU 2017 suite. What we see here is all the benchmarks that we have looked at and the RISC-V instruction type, for example, a NAT instruction. And what we do here is we normalize all those instructions per benchmark and cluster them. So this basically shows you how similar the instruction footprint of every single benchmark is. So the lower the benchmarks are connected together, the more similar the instruction footprint is of those benchmarks. So then you can, for example, see that GCC and ProBench, they are executing pretty similar instructions relative to SIEM. But let's, yeah, I just want to point out LBM is kind of very, very different from all the other benchmarks. And if we do the same thing after time, right? Before we just did it after the count. And now we look at, okay, how do the different RISC-V instructions compare in time? And you can see if the clustering completely changes. So that means it's not just enough to look at the count of retiring instructions, but also at the time. What's interesting here is LBM is, again, it's very alone in this whole stack. What we also can see that, again, yeah, in the next slide, I'm going to compare it to the nearest neighbor Paris to show you why that is the case. But we also see that GC and ProBench are, again, very near to each other. We also see why in the next slides. So have a look at the top 10 instructions with the closest neighbor of Paris and see why LBM is such a lone wonder, why it's so alone. On the left side, you can see the top 10 LBM instructions. And the darker bar is LBM and the lighter bar is Paris. It's the normalized time that this benchmark has spent at each of those instructions. And you can see that they are quite different. Only the floating point load instruction is both execute this instruction, and Paris even spends more time relatively seen on this instruction. But overall, you can see that they execute these instructions with very different times. On the right side, you see the same thing for Paris compared to LBM, and you can see that the top 10 instructions from Paris are for sure not the top 10 instructions of LBM. So that's why they are different. And we can have the same look at GCC and ProBench. And here you see the top 15 instructions of GCC and ProBench, and you can see they match up pretty closely. Okay, I want to also show you another great thing that we did with TraceDoctor. So we attached the trace vector to all the necessary informations in our paper. And we implemented statistical performance profilers out of band in TraceDoctor as workers. And what that allows us is to run one simulation and attach a lot of different statistical profilers to this one simulation and let them run out of band and model those statistical profilers in parallel to the simulation on the fly while it's running. That allows us to not only simulate many different profilers, but also the same profilers and with different sampling frequencies, for example, at the same time during one simulation. And that saved us many, many simulation runs. If we would have done the same evaluation in serial, we would have spent $170,000 on AWS. That's also my professor now. So we were happy. Yeah, so in conclusion, TraceDoctor offers a really high performance tracing interface for FireSim. It's flexible, versatile, and saves time and money. It's the first, to our knowledge, that enables end-to-end tracing of full stack benchmarks, a full stack environment with industry's benchmarks end-to-end. And TraceDoctor is featured in TIP, which got the runner-up award as Micro 2021. And also we will publish time proportional event analysis at ISCA 2023 this year. And yeah, TIP is TraceDoctor is open source. It's ready to be adopted by you and maybe also FireSim in the future. Yeah, thank you.
Any questions?
So you mentioned that the workers, I guess, so the trace coming from the simulated world to your TraceDoctor doesn't have to necessarily adhere to the tracer respec or the committed instructions. It could be anything that's marked on the machine.
Yes, it's a general bit vector that you can just attach to whatever.
So that's great to know. The question that's built off of that is, it seems like right now that bit vector is basically passed to all workers, so all workers see the same bit vector. Do you think it would make any sense to basically split up that bit vector amongst different workers so that workers only like work on chunks of the data? So basically, like I'm saying, if some signals basically fire at different rates on a simulated machine, then you can basically have workers work asynchronously with respect to one another on different parts of the vector. I don't know if that helps or.
That's actually super interesting. Like in the performance evaluation where we compared the text output with TracerV, and we created those 3 different workers, right? They all saw all the tracing data. But what we did is we just said like the first worker is doing every third, right? From the first on, the second one is from the second on every third, and from the third every third. So they were skipping themselves packages that they were seeing. But yeah, it would absolutely make sense to also provide a feature that you can distribute tracing data differently among workers. That would be for sure an interesting addition. Yeah. So,
seems helpful for like simulation throughput, right? So
yeah.
If you know one signal fires a lot more, you don't have to pause the simulation as much. You
yeah.
can let that signal basically go to that worker whenever it comes.
But also the highest benefit of TraceDoctor is the TracerV, right, pulls in the data from the simulation, processes it, and then the simulation continues. TraceDoctor does not do that. It pulls the simulation, the data from the simulation, and everything afterwards is done in extra threads. So the simulation can immediately continue. Only if the workers are not fast enough to keep up with the tracing data, the buffer queue fills up. Yeah.
So is there any reason we shouldn't just replace TraceDoctor with this?
No, not really. We should maybe merge it so that the trigger system and everything, yeah. But no, I don't see a reason why not replace it.
Good. I look forward to using it. Yeah. Any other questions?